Welcome to the deep dive. Today, we're heading out, way out to Mars.
Yes, there's some really fresh evidence coming back from NASA's Curiosity rover.
And it seems to be shaking things up a bit regarding Mars's ancient history.
That's right.
So if you're looking to get up to speed quickly on this, you're in the right place. This is a big one.
It really is. We're talking about a study just published in Science,
Science, okay, top journal.
and it focuses on what Curiosity found drilling into Martian rocks. Tiny samples, huge implications.
Right. So our mission for this deep dive, figure out what this new data tells us about, well, early Mars. Was it warm, wet,
Right.
maybe even habitable?
And crucially, if it was like that, what happened? Why is it the cold, dry place we see now?
Exactly. Let's jump in. Where did Curiosity find this?
Okay, so between 2022 and 2023, the rover drilled samples. 3 different spots,
Whereabouts?
all within Gale Crater, that massive impact basin.
With the big mountain, Mount Sharp in the middle.
Yeah, exactly. And the analysis of these rock samples, it turned up something quite interesting, which is a mineral called siderite, and quite a bit of it.
Siderite. Okay, I've heard the name, but remind me, what is it exactly?
It's an iron carbonate mineral. So iron, carbon, oxygen, all bonded together.
Carbonate. That sounds important for atmospheres, maybe?
Bingo. It forms in sedimentary rocks,
Yeah.
rocks laid down by, likely, water billions of years ago.
So finding it tells us about the conditions back then, when the rock formed.
Precisely. And it wasn't just a trace amount.
How much are we talking?
In some samples, up to 10.5% by weight. That's a lot.
10%. Okay, that does sound significant. So what does that amount of siderite imply?
It strongly suggests that ancient Mars had a much, much thicker atmosphere than it does today.
Thicker and full of what?
Carbon dioxide, CO2, a lot of it.
Ah, okay. CO2, the greenhouse gas.
Exactly the same principle as here on Earth. CO2 traps heat.
So a thick CO2 atmosphere means a warmer early Mars.
Considerably warmer, potentially. Warm enough, perhaps, to keep liquid water stable on the surface.
Which fits with all those other clues, right? The features that look like old riverbeds, lake shores, maybe even ocean coastlines.
It connects those dots beautifully. We see evidence for water, but Mars is currently freezing. How is that water liquid?
A strong greenhouse effect from CO2. This siderite seems to be the smoking gun for that CO2.
It's very compelling evidence for it, yes.
Yeah.
And if you have stable liquid water for long periods,
Then the potential for life, at least microbial life, goes way up.
it becomes a much more plausible scenario based on what we know about life needing liquid water.
Okay, but here's the big question then, the one that's always bugged scientists, right? If Mars had all that CO2, where is it now?
That is the multi-billion-dollar question, the long-standing mystery, as the researchers put it.
Because today's Martian atmosphere is incredibly thin, almost no CO2 compared to what would be needed.
Right. Climate models for a warm, wet, early Mars require huge amounts of CO2. So the prediction was we should find carbonates everywhere.
Carbonate minerals, formed when atmospheric CO2 reacts with rocks and water.
Exactly. The CO2 gets locked away chemically into the ground.
But we haven't really found them everywhere, have we? Previous missions, orbiters. The carbonate hunt has been a bit disappointing.
It's been surprisingly difficult. Limited detections, nothing on the scale predicted by some models.
Which made the whole warm, wet, early Mars idea a bit tricky to sustain. If the CO2 wasn't locked in rocks, where did it go?
Well, the prevailing theory remained that it must be locked in rocks somewhere, transitioning the atmosphere from thick to thin. We just hadn't found the main reservoirs.
So does this siderite discovery in Gale Crater, is this potentially part of that missing reservoir?
That's what makes this finding so significant. The sheer amount of siderite suggests, yes, substantial CO2 is being pulled from the atmosphere and locked into these specific rocks in Gale Crater.
Is there reason to think this isn't just a local thing, just specific to Gale Crater?
That's a key part of the study, the types of rock formations Curiosity sampled here. Similar formations have been identified by orbiters across Mars, globally.
Ah, okay, so the researchers are suggesting...
They're hypothesizing that these other similar regions might also be rich in carbonates like siderite.
potentially holding vast amounts of that ancient Martian CO2.
Potentially, yes. We could be looking at a global phenomenon, a major piece of the puzzle of Mars's lost atmosphere.
Wow. So this isn't just about finding a mineral, it's about understanding a planet-wide environmental shift, a huge transformation.
One of the researchers, Edwin Kite, actually called it the largest known environmental catastrophe, a shift from potentially habitable to, well, what we see today.
And he stressed figuring out where the carbon went is key.
Absolutely. Because the carbon cycle dictates the climate.
On Earth, our carbon cycle is dynamic, isn't it? Volcanoes release CO2, oceans absorb it, rocks get subducted and recycled through plate tectonics.
Right. It's a complex system with feedback loops that generally keeps things relatively stable over long time scales.
But Mars, it doesn't have plate tectonics, does it?
Nope, no evidence for it. So its carbon cycle would have been very different. Simpler, perhaps.
And this study suggests, what about the Martian cycle?
The findings point towards an imbalance. It seems like the process of sequestering CO2, pulling it out of the atmosphere, and locking it into rocks like siderite was happening much faster or more effectively than any process releasing it back into the atmosphere.
So unlike Earth, where things get recycled, Mars had more of a one-way street for carbon, down into the
That
rocks,
seems to be the implication here, a runaway sequestration process.
which would inevitably thin out the atmosphere over geological time.
Exactly, leading to cooling, loss of liquid water at the surface,
hmm
the end of that potentially habitable era.
So understanding this siderite, its abundance, how does that help going forward? What's the next step for researchers?
Well, this quantitative data, knowing how much siderite is there, can be plugged directly into climate evolution models for Mars.
Ah, so making the computer simulations more accurate.
Precisely. We can refine the models to better match the geological evidence. It helps us understand the timeline better. How long could Mars have stayed warm and wet? What were the key turning points?
It helps pin down the why and when of Mars losing its habitability.
Yes. And it raises fascinating questions about planetary evolution in general. Was this fate inevitable for a planet of Mars's size and geology?
That's a big thought. So let's wrap this up. The key takeaway.
Curiosity's discovery of abundant siderite provides really strong support for that idea of an early Mars with a thick CO2 atmosphere warm enough for liquid water.
And crucially, it points to where a significant chunk of that missing atmospheric carbon might have ended up locked away in carbonate rocks.
It's a major piece fitting into the Martian puzzle, a real aha moment for the field.
It definitely fuels the imagination about early Mars and maybe, just maybe, early life.
It certainly keeps that possibility very much alive.
So the final thought to leave folks with, if Mars did have all the right stuff, what exactly tipped the scales? What caused that irreversible shift?
And could understanding the planetary catastrophe on Mars teach us anything about the fragility or resilience of habitable environments elsewhere?
Including our own planet. Definitely something to keep thinking about. Thanks for joining us for this deep dive.